Okay. Yeah. Can you see this? Yes. So these are the exercises in the first part of the course before we started talking about the Ito process, which we will continue today. So there are two chapters involved from Whale Port Stone, chapter 4 and 5, and these are the exercises from them. The problem number 1 to 20 from chapter 4 and problem number 1 to 5 from chapter 5. And we have also we have covered some material from chapters 2 and 3 of Occidental. And the exercises I want you to do are these two, 10 and 12 from chapter 2 and 1, 2, 4, 5, 6, and 18 from chapter. All right, so did you all see this one? Are you seeing my screen now?
Yes, sir.
Okay, so these are the exercises so far. I will add on as I move ahead with them. Okay, so now let me resume our discussion from last week. We were talking about the Ito process. So now can you see the other PDF? This is slightly dark, so I don't know how visible it is. Is it okay?
Yes, sir, it is okay.
So we were actually discussing the general formulation with which we want to go ahead with our stochastic integral theory, and of course the stochastic differential equation solving exercise. And this class we call the Ito process, which are of the form dxt equal to udt plus vdbt. So this is the notional representation, but which is below here. But the actual representation is above, which is actually the through the integral. So xt will be integral of uds and integral of vdv. And the first canonical example that we looked at was this integral that we evaluated from first principle. So d of half bt square is half dt plus bt dvt, from which we essentially arrived at the integral of bt dvt. And as this works as an example because here I have two differentials, one dt and other dvt. So the integral will involve two terms. So what we really want to know is whether this result is really generalizable for this particular class of functions, where in my integrand the v has to be square integrable finite. So it has the square integral must be finite with probability 1, and the u function in the dt integral must be ft adapted. This is where we stopped last time. So before I continue, are there any clarifications that are needed? And I said that some of these constructions we are not going deep into the theory. We are just giving an overview here. But if you are interested, you can always look at that excellent book by Karatsas and Shreed, which Shubhrajyoti has quickly shared with us. So Shubhrajyoti, is that the whole book that you shared the link?
Yes, sir, it is from Google eBooks. So,
It's the whole book.
yes.
Okay, so great. So anyone, so has anyone actually opened the book yet? No, I am not expecting.
No, sir.
I know because this weekend was placement weekend, so I know you, or many of you were quite busy. But It is a very, very nice book. I did not put it in my reference list because I thought that it's a bit too theoretical. But for all the theoretical queries that you may have, which are not covered in detail in Oxendale, because Oxendale and Whale-Portstone both are like practical kind of books. So they focus more on application than on the nuances of the theory. So they also say that there are some theoretical issues which we are ignoring here, but you can always look up elsewhere. So Karadza Century is an excellent reference for all those theoretical questions. So in particular, if you get on to an academic career in mathematical finance, you want to develop new financial models, then Karadza is going to be like your Bible. Okay. So any questions before I move ahead? Okay, so no questions yet, which means you have not read the material yet, which is not good, but I can estimate that. And also some of you have not turned in the first assignment. I have checked the Google Drive and my email. So I think 8 or 9 people are still left to submit the first assignment. So you should try to do it by midnight today. So I can wait for it for 24 hours, but after that I will have to penalize. I don't know that those who have submitted, those who have not submitted are here today or not, but just pass on this information that you have 24 hours leeway. After that, the full marks will get reduced. Okay. So now let us get on to the business for the day, which is the closure of the DTDS combination under integration. So the result is known as the Ito formula, which is actually a theorem proved by Ito. It is called the Ito formula, and this is like the building block for the Black-Scholes formulation in mathematical finance and many other formulations actually. This works as the backbone. And this result is actually an application, a very, very nice application of the Taylor series idea. So again, we are looking at finitely many terms in an infinite expansion. We are ignoring the higher order terms. And given that we know that we are working with the normal distribution, our interest is basically in evaluating the first two moments. So whether you think of it in terms of the Taylor series or the characteristic function or the moment generating function, the intuition is the same, that you actually have an infinite series where higher order terms can be safely ignored. So the formula or the theorem says the following, that suppose xt is a process of this form. So xt is of this form, dxt is udt plus vdbt, or xt is actually a sum of these two types of integral. So that's any xt process. And let us take a function g. The function is a function of time and as well as x. So it can be explicitly a function of time, in addition being a function of x. And I assume that it's a sufficiently smooth function. It's a C2 function on the time domain and the real line, which is the domain for our x process. Okay, so C2 is familiar, C2 is okay.
Yes, sir.
So I call yt as the resultant process, g of txt. Okay, so xt is the original Ito process and y is a transformation of x. Y is g of txt, and the theorem says that if xt is an Ito process of this form, then yt will also be an Ito process. And of course, then I should be able to say what is the u and v for y, and that is given by this result here, that dyt, again in the differential form, dyt will have this expansion. So the dt term is del g del t, the dxt term is del g del x, and then I have a second order term which is of the order of dxt square, which is half of del 2g del x square. Now, if I were interested in only a deterministic kind of expansion, then I would have stopped after dxt. That would be the first order approximation. Because I also have the randomness to take care of, I include this second term, which is essentially like the variance term. And we already have discussed this before, but maybe not formally written it down, that we know that the order of this term dxt whole square is actually of the order of dt. So that the usual formula for stochastic differentials are the following, that if I consider the other products like dt times dt or dt times dbt or dbt times dt, all these other products are zero. They can be ignored safely. They are of the order of a smaller order than any of these terms, and hence we ignore them, like in the Taylor series approximation. The only difference is in the dbt term, because the variance of dbt is of the order of dt. So dbt dot dbt is evaluated as dt. And as dxt involves all these combinations, because dxt will have, so when I do dxt dot dxt, as in here, I will have all four combinations. So they are to be evaluated using this formula. So is this correct? Is this okay? Because again, I'm not getting into details, but we have discussed about the intuition of this thing before when we constructed the differential, stochastic differential from the Brownian motion properties. So dt dot dt being taken to be zero is no surprise. That's what we have been doing for deterministic calculus. But these other two terms, dt dot dbt or dbt dot dt, in whichever order, they are also of a smaller order and can be taken to be zero. That's something that we have discussed earlier, but if you have any doubts, you can ask. And this fourth term, of course, as we discussed, that comes from the variance idea, and that is of the order of dt. So that will be retained in the expansion because it is same as the first order term here. So if I evaluate this dyt now, because I have a dxt here, which I can expand, and I have a dxt dot dxt, which also I need to expand, I will finally get this following expression. So if I write it down completely and then collect terms, some of the terms will vanish, of course. I will get dyt equal to, so the coefficient of dt, so the u for the u function for y, that will be del g del t plus u del g del x plus half v square del 2g del x square. Now these first two terms, they are coming from this term here and the dt term here in the dx. So these are the first two terms. They are coming from the actual first order terms. But this third term here is actually contributed by this term here. So this half del 2g del x squared term comes here, and this is the only term that survives. All the other three products in dxt dot dxt will vanish. So I have no more dt terms coming in from anywhere else. So these are the dt terms, and of course dxt also has a dbt, and that dbt comes here. So that's the only dbt contribution, v del g del x. So is this clear? This is a simple arithmetic. The real details are all collected in this expression here, where I can safely stop and say that this is again an Ito process. But that, of course, we are not going to discuss in detail. Again, if you are curious about how the proof works, you can look at Oxendal. Oxendal has a simplified version, and you can also look at Karadzias and Shreve, which has more details. But coming from this DYT expansion, the second step is pure arithmetic. So is that clear to all of you?
Yes, sir.
So this is our ethos formula. So the ethos formula that we keep using in finance all the time is essentially this last equation, which is called D.10 here. So this DYT expansion is what we are going to use all the time. So what we have done is we have looked at a particular kind of process, which is a sum of two integrals or sum of two types of differentials. And we have this very useful result that this form is closed under integration or differentiation. In fact, it works both ways. It is closed, and I have an explicit formula for evaluating the new dt and dbt coefficients from the original u and v using the ethos formula. So this is what we have, and this is the main toolbox for our Black-Scholes methodology. Before we go to that, again, just a quick reality check. Some of the integrals that we have done earlier from first principles, now we can check quickly whether they match the Ito formula. And also, if I have a new integral, which I want to evaluate swiftly, I can again use the Ito formula and find out the integral with little bit of level. So first example is this one. We have done it before, integral bs dvs. So I choose xt equal to bt. So basically I choose u equal to 0 and v equal to 1. And the function gtx is chosen to be half x square. Of course, in this case, the function is independent of t, directly, not dependent on t. So if I choose my gtx as half x square, so yt is half bt square then. So I use the ethos formula directly on y, and I have dyt equal to bt dbt plus half dt. This you can quickly check from the ethos formula here, because some of these terms are not there at all. So u is 0, so life would be much simpler. So do you see that dyt is actually bt dbt plus half dt? Is that clear? Because here the first two terms will vanish. Just check this quickly and satisfy yourself that we are on the right track.
Yes, sir.
Okay, great. So that would mean that d of half bt square, so yt is half bt square, so d of half bt square must be bt dbt plus half dt. And then I integrate on both sides. So I have the integral checking out. So the first example checks out that integral bs dvs is actually half bt square minus half t. We have done it before from first principles, but now ethos formula gives us a very quick way. So as I said, once we have ethos formula, it's like I have already established the integral of sin x formula and other typical formula. So this one is the first one. So it checks, we know it is consistent. A second example, quickly, integral of s dv. So now I have an s term here. So my candidate for g function is tx. So this takes a little bit of practice sometimes, that what is the choice of the correct choice of the g function. But if you look at the integral, typically you will be able to guess what is the right g function, and then a straightforward application of the ethos formula usually gives you the result. So I take gtx equal to t times x, which means yt is t bt. So again, I apply ethos formula, dyt is bt dt plus t dbt. When we check with the actual formula and evaluate, this will be dyt. So I integrate both sides. So the left hand side I will recover TBT, which is integral of dyt, and this side I will have bsds plus sdbs. So I can change sides and I can see that integral sdbs is TBT minus integral bsds. Well, we have not been able to evaluate this explicitly, but we have got something else which is also useful. If you look at this example closely, this is a restatement of our integration by parts formula that we learned in deterministic real calculus. And if you, for the time being, forget about the stochastic nature, you will see that this is actually what you would expect. If integration by parts were available to you, then this is what you would expect. So this example is actually taking us to the following result, which is again going to be useful for us. This is an example, but I can actually generalize this thing in the following way, that which we state as a theorem. This theorem is the integration by parts result, that suppose I choose a function f s omega as a deterministic function, only a function of s. So fs omega is just a function of s. There is no omega here. And that function is continuous and bounded on the time domain, the relevant time domain, here say 0 to t. Then if I want to evaluate this dv integral 0 to t fs dvs, that dv integral can be written as ft bt minus integral of bs dfs. So I have transformed a dv integral into a dt integral, because dfs will only be a dt integral because the function f has been chosen to be non-stochastic. And it is crucial that f is non-stochastic. F does not depend on omega. And we already know that this kind of integrals, bs dt type integrals, bsds, they are Gaussian in nature. So they are Wiener process. So because of this equality here, all these fs dvs type integrals will also be a Wiener process, and they will have the normal distribution. So that's the big advantage of this integration by parts result, that it not only gives us an operational formula for evaluating integrals, but it also gives us the Gaussian property to be inherited to the fs dv type integrals. So again, is this clear? Is the intuition clear? Because again, I am not going to prove the theorem, but we have seen this theorem in the deterministic version before. What we are saying here is the same intuition will go through for the stochastic version. So is this clear to all of you?
Yes, sir.
So I have an integration by parts result, which we motivated from this particular example. This in order to evaluate this kind of an integral, SDB integral. And we showed that dB integrals can be transformed into DS type integrals. That's the integration by parts. And because of the Gaussian nature of the DS type integrals, we can now claim, or we can now prove, that the dB type integrals, FSDB, those integrals will also be Gaussian. So our processes to be considered still remain to be the normal distribution, which is very, very useful. Okay. So we have the Ito formula then, which is our mechanical operational tool for evaluating stochastic integrals. And we also have an integration by parts formula, which allows us to convert between ds and dv integrals. Because ds integrals we have already learned how to evaluate quite a bit. So evaluating dv integrals will become easier because they can be converted. So we come to the Black-Scholes result. We have all the toolbox, all the tools that we needed to use have been developed, not entirely in the theoretical sense. We have glossed over or omitted many of the details, but at least the intuition, I hope, is clear to you. So we have the background toolbox, the ethocalculus toolbox, and of course the financial intuition that we have already learned in the discrete setup. All that intuition is still going to be relevant. Using these two things together, we are now going to look at the Black-Scholes differential equation, which is like the normal distribution in statistics or the binomial model in the discrete time models. And again, we will be discussing some of these issues, but this MIT lecture note that I already supplied the link for is also a very nice material. So in the MIT lecture notes that I have already shared with you, I have shared the links with you. There are lectures on Black-Scholes pricing, and they are actually quite detailed, quite nice. So you should also take a look at them. Okay. So what are the financial principles that we are going to use again? So first and foremost, the Black-Scholes model will rely on the no arbitrage principle. That has been like our bedrock. We always want this financial market to have no arbitrage opportunities. That's how we define an efficient market. So that would still come and remain with us. And how are we going to use that no arbitrage analysis? The Black-Scholes model is developed using a stock and an option or any other derivative on that stock. So remember that even in the discrete time models, we looked at combinations of things and we did no arbitrage valuation. To evaluate a call, in fact, to prove the put call parity result, what we did was we looked at some cash and the call option on one hand, that was a portfolio, and the stock and the put option on the other hand, that was the second portfolio. And we showed that these portfolios have the same value in all states of nature, and hence their day zero price has to be the same. Do you all remember this? So the put call parity.
Yes, sir.
Yeah. So that is the same kind of idea that we are going to use now, and our combination will be a stock and some derivative. Say let's say call option on that stock, and we will use the no arbitrage principle in an infinitesimal time interval. Earlier, when we were in the discrete time model, we didn't have to make that idea clear because time was discrete. Everything happens at discrete time points. So anything in between, no changes are going to happen. But now that we are in the continuous time world, changes can happen anytime, differential changes. So we have to also think of infinitesimal time intervals. Okay, so fine. So let us see how it goes. We will come to the details. And we are still going to assume that single factor model, that there is a single source of uncertainty. So again, recall that we defined the stochastic integrals for multi-dimension, because I said that there are some applications where we have multiple sources of uncertainty. We discussed it very, sorry, we discussed it in summary, in a nutshell, but I mentioned that it is possible to extend our integration theory to multiple dimensions. But most of our applications, we will stick to single dimension. So one single source of uncertainty, which in financial terms relates to the single factor model. So we still keep working with the single factor model, and we use the no arbitrage analysis in infinitesimal time intervals. So what we are going to construct then is a portfolio. We are going to show that there is a portfolio using this combination of stock and the derivative that is riskless for an infinitesimal time interval. So that's what our final objective is going to be like. So let's see how we do that. So what are the basic assumptions? The basic assumptions, of course, the stock price follows an Ito process, because that's the canonical process we are now considering. We are not only talking about Brownian motion here, we are talking about that particular combination. So our stock price process has to be a sum of a dt and a dv component. There is no restriction on short selling, which means any kind of negative weightage on a particular asset is allowed, because for now, to begin with, we want to keep it as simple as possible. So we want to do an unrestricted optimization. So we do not put any restriction on short selling. Of course, it's not realistic. Later on, for real life applications, we will have to put restrictions, but to get the simple model clear, we have to start from a very simplified scenario. We are also assuming that there are no transaction costs, because if there are transaction costs, then some of the profits get dissipated. So I make the profit and then I have to pay for the transaction, so my profit gets lower. So then my no arbitrage analysis has to be modified accordingly. So if I know that the profit that I finally get is less than what I can get in theory, then I have to allow for that and make changes in my portfolio choice. That would make the mathematics of this whole model more complicated. So to begin with, we assume no transaction cost. We assume perfect divisibility, which means I can buy or sell any fraction of any contract or a stock. So there is no granularity in the market. I also assume there are no dividends during the life of the option, the lifetime which I am going to consider, because again, you remember the dividends make the formula more complicated. So let us begin with no dividends. And of course, the market does not allow any arbitrage opportunities. Market is efficient. Trading can be done in continuous time, which means there is no lag. As soon as I click the mouse, the trade immediately gets transacted, which means the market is open. And finally, I assume a constant rate of interest for all maturities. So whatever my investment horizon may be, I always get the same constant rate of interest. That is also a simplification, but again, we initially take all these simplifications to make the mathematics as clean as possible. We want to get a clean formula, and then we will gradually build on that formula by allowing these other factors in a more realistic way. All right. So are these assumptions clear? We are actually taking many assumptions. Some of them are similar to the discrete time model assumptions: no transaction cost, no dividends, efficient market, constant rate of return. These we have, or unrestricted short selling. These are inherited from the discrete time model. But because we are in continuous time now, we have to take a few more assumptions. first and foremost is that the stock price follows an Ito process. And also we say that there is no lag between the decision and the execution of a trade. So trading is continuous. So again, are these assumptions clear? Because these are non-trivial assumptions. Most of them are not true in the real life stock market. But for a clean analysis, for a nice modeling exercise, as we have been doing in statistics all along, we need a lot of assumptions.
31 10ची 8 11ची त्याच्या आधीचं माहिती.
Hello? What happened?
मग
Sir, in perfect divisibility, can we trade half the stock?
Yeah, I can trade any real number. That's what I mean by perfect divisibility. Any real number.
तरी जाऊन आजूबाजूला जिथे
So again, this is not realistic, but for the time being, this is the assumption we work. You see, because I am working with the differential equation, so I need to know what kind of differentials I am allowed to use. So I guarantee myself that I can use any differential. There are no gaps. Okay, so there are some discussions written here, which you can go through later on if you want. But the basic setup that we are going to look at is the no arbitrage analysis in continuous time model. And the objective is to create a portfolio that is riskless for a very short time interval. So we will see how we can do that. And to do that, we take quite a few assumptions, and then we use the ethos formula. Okay, so our construction process is the following. The construction process is, look at the stock price process. ST is the generic name for the stock price. So the changes in the stock price is DST. The model for my changes in the stock price is in the logarithmic scale. So if you look at this particular equation, you should be able to see that this is actually modeling changes in the logarithmic scale. So I am not really modeling DST. I am actually looking at D of log ST. So my model is DST by ST. So I can write this ST on this side, or I can divide DST by ST. So that is given by mu times dt. So this is the dt part. This is my u function, mu, and sigma dbt. This is the volatility part, drift part. Sigma is the v function. And for the initial application, we assume both mu and sigma to be constant. So this is the simplest possible Ito process to represent the stock price change. So DST by ST is mu dt plus sigma dbt, which of course I write it like this. DST is mu ST dt plus sigma ST dbt, but it's the same thing. So the model is essentially the logarithmic model. So what I am really going to drive at is the log normal distribution for the stock price. So I am going to model the logarithm of the stock price using the normal distribution with the dbt term. Okay. Clear?
Yes, sir.
So these kind of Ito processes are called geometric Brownian motion models, because if I take log, then it becomes a Brownian motion. So it is like the connection between normal distribution and log normal distribution. We all know that. And also we fix some time horizon. We are not going to work with infinite time. So we consider our stock price process over some finite time interval, 0 to say capital T star. But as we are going to be really interested in small time intervals, that finite interval is not going to play a role all the time. So we are actually going to look at changes over small intervals of time. So this is my generating equation. It's a linear stochastic is linear SDE of this form. And now I want to use the ethos formula. So I know that if I write any contract on the stock price, any derivative contract on the stock price, it can be represented by a function f of the stock price itself and the time. So fst, if I am able to evaluate this function, that will give me the price of any derivative contract that I want to define on the stock price. Okay, is this connection clear?
Yes, sir.
So think of any derivative contract arrangement that can be represented through this functional form. And then what I need to do is I need to evaluate that function. And evaluation means pricing. So the price of this derivative contract FST I want to find. All right. So now this is a ready-made candidate for ethos formula. So if DST is of this form, then D of FST will be of this form. Direct application of ethos formula, I will have this DT term where there are 3 components and the DV term with a single component. That is easy. We have done it before. It's not complicated. In fact, the details are here, but you can just do it quickly. So the important part is, if I have DST given by this geometric Brownian motion model, then DF is given by this model. Now, what is my portfolio? So I construct a portfolio, I call it pi. My portfolio is, I go short 1 unit on the derivative contract. So it's -1 weightage on F. So I go short on the derivative contract, and I buy del F del S amount of the stock. That's my portfolio. Del F del S units of the stock and -1 unit of the derivative. So again, I can easily evaluate d pi because I know ds, I know df. These 2 things together, I can evaluate d pi. And you see, what I have done is, I have chosen the weightage on the stock price in such a way that d pi here does not have a dB component. So if you evaluate d pi explicitly, writing down the expression for df and ds, add things up, you will see that I have chosen this del F del S precisely to cancel out this term here. I want to make this expression free of the dB term. Okay, is it clear? So my choice of the coefficient on the stock price, the amount of stock I am buying, has been deliberate. It is chosen so that in the final expression of d pi, there should not be any dB terms. Is this clear to all of you?
Yes, sir.
So in fact, after simplification, the d pi is given by only this thing within brackets times dt. So all the other, most of the other terms will remain, del F del T, half del 2F del S square. But some terms will get cancelled, and most importantly, all the dv terms cancel each other out. So d pi has no stochastic component. And if for any portfolio there is no uncertainty involved, so no stochastic component means there is no uncertainty involved in the return for this portfolio. So d pi, the change in pi, is deterministic. And I have the efficient market principle that no arbitrage is possible. And under that condition, a riskless portfolio, so this is a riskless portfolio. There is no uncertainty. A riskless portfolio can only give you a return equal to the bank rate. Is that clear? That any riskless asset can only have a rate of return equal to the bank rate in an efficient market.
Yes, sir.
Because otherwise there will be arbitrage opportunities.
Yes.
So good. So that means at least for a very short interval of time, because I know that this is a differential expression. So this differential expression does not have constant coefficients. So these coefficient values are going to change in a little while. Okay. So at least in a very small, short interval of time, I can consider this d pi to be deterministic, which would mean d pi must be equal to r pi dt. That is the bank rate return. So I have this asset pi, it is riskless. So in a short interval of time, dt, the return must be at the rate of r. So that is the crux of the matter in the Black-Scholes evaluation model. The operational formula I have from the Ito's result, but the equality comes from the no arbitrage principle. That this expression here, which is evaluated from the Ito's formula, must equal r pi dt because of the no arbitrage opportunity situation. So then I have this following equality that r pi must be equal to minus of this thing within the bracket. So this term equal to this term, the two coefficients of dt. And then I insert the expression for pi, because pi is actually two things, short on the derivative and del f del s times the stock. So I have minus rf plus del f del s rs, that is inserting pi, equal to this expression on this side. So I change sides, and finally I can write this particular differential equation. Note that very importantly, what I have here is a differential equation, not a stochastic equation. So del f del t plus del f del s rs plus half del 2f del s square sigma square s square equal to r times f. And this is the beauty of the Black-Scholes formulation. The original stochastic differential equation nature of the stock as well as the derivative should have generated a stochastic differential equation. But then we impose the no arbitrage condition on a particular choice of portfolio, so that our stochastic differential equation is reduced to a differential equation, which I can easily solve. So if you have done any course on partial differential equations, you should be able to recognize this as the heat equation. So there are different names for this. I think sometimes it is called heat equation. Some context is called the Fokker-Planck equation. There are many names for this particular PDE. It's a PDE because F, remember, is function of two variables, t and s. So it is actually a PD, partial differential equation, but non-stochastic. The important part is that it is non-stochastic. And of course, we have to specify suitable boundary conditions, and boundary conditions will come from the contract specifications. But once we have the boundary conditions, we can uniquely find the solution of this particular PD. And because we recognize it as the heat equation, we basically know how to solve these things. There are textbooks which discusses how to solve heat equation. So I will take a break here. We will resume in roughly 30 minutes. I suggest that you look at this material, what we have covered so far, because this is the crux of the continuous time model in finance, the Black-Scholes formula. We will discuss it more after the break, but just go through it once, see whether logically things hang together. Of course, theoretical details we have omitted. So as I said, you can look for it elsewhere. I have given you the reference, but intuitively, particularly from the financial market intuition point of view, whether this whole story sounds consistent or not, that you should check and satisfy yourself. Okay, so we'll take a break and we will maybe start at 11:55. So good. So before I resume, any questions so far? So we have actually arrived at the Black-Scholes formula. So are there any questions?
Sir, if we choose another type of pi so that d pi is non-stochastic, then would it resolve become the same equation or something else?
If we choose a d pi where there is a dB term, non-zero dB term, then we cannot use the no arbitrage condition.
Yes, no, I'm saying that if we choose another choice of pi so that d pi becomes non-stochastic.
Oh,
Like,
no, but then the law of one price must hold.
yes, but that would give me another set of differential equations instead of this one.
Possibly, but if I then impose all the boundary conditions that are relevant for that contract, so if you take a different combination, that means you are using a different portfolio, some
Yes.
other derivative contract, something like that. But then the boundary conditions must force you to the same pricing equation.
Okay, okay.
Because we still have no arbitrage principle.
Yeah.
Sir,
Yes.
we are trying to get rid of DB term to reduce the arbitrage opportunity, right?
We are trying to get rid of the DB term to invoke the no arbitrage opportunity. The no arbitrage opportunity I'm comparing with the bank. And because bank has no DB term, I want to create a portfolio which does not have a DB term, at least in a short interval of time.
And the zero risk thing, we are assuming it or we are getting it through
No.
this differential.
No. We are not assuming. We are eliminating the DB term. That gives us a zero risk portfolio. The source of risk is the DB term. So I want to create a linear combination so that the DB terms get cancelled out. Did you get my point?
Yes, sir.
So the whole objective of the exercise was to create a linear combination so that the DB terms cancel each other out. So that we have a portfolio with only DT term, and then I can match it with the bank. Then I can invoke the arbitrage principle and say that it must equal the bank rate, and hence I get the differential equation. If I create a different combination, as Subhrojyoti said, that might be possible, but then again, I'll have to use the no arbitrage condition there.
Yeah, so if my portfolio is stochastic, then
if my portfolio is stochastic, then I cannot compare it with the bank. I want a easy strategy of solution. This strategy was create a riskless portfolio so that I can equate with the bank.
Yeah.
So it's a clear case of back calculation. You want to create a riskless portfolio. Why? Because a riskless portfolio can be equated with the bank rate through no arbitrage principle. How do I create a riskless portfolio? I want an equation with no DB term. Okay. Then how do I create that? I have to choose my coefficients in a clever way so that the DB terms get cancelled. That's the whole exercise in the Black-Scholes analysis. Any other questions? So I want to discuss a few simple examples because simple examples are easy to show and difficult exercises you can do yourself later on once you know how to work with this. So the easiest example that I am going to talk about is first a forward contract. So if I take a forward contract, now remember that forward contract has to be executed. So it's not an option. So what I do is I fix a price for the stock at a future date. So suppose that price is capital K, which we call the strike price. So at maturity, what we do is I pay that amount K and I get the stock. So then again, the risk neutral valuation principle will give me the day zero price of that forward contract, and the day zero price of that forward contract will be given by this formula, that the current stock price minus whatever money I need to keep in the bank now so that I will get K amount of money at capital T at X bank. So that's how we actually evaluated a forward contract, and we did it directly. We didn't need any Black-Scholes equation. But if I were to formally use the Black-Scholes setup for this equation, then I can quickly check whether the Black-Scholes analysis is consistent with our first principle analysis. So for this forward contract, our F function is exactly like this, S minus K discounted. So del F del T will be given by this expression here, del F del S, del 2F del S square. So my Black-Scholes PDE will work out to the left hand side will be equal to this term and the right hand side will be equal to this term. And if you now check that these two sides are exactly the same. So even if I use the Black-Scholes equation formally to evaluate a forward contract, I would get the correct risk neutral valuation, whatever I should. So the left hand side and the right hand side will both check out. So it is like the checking that we did for the simple option earlier for checking whether the ethos formula works well. So that was earlier today. Okay. So this is a trivial example where we don't need the Black-Scholes, but we just wanted to check whether the Black-Scholes gives us consistent result. But if we move on to a call option where we really need some calculations to do, we can actually use the power of the Black-Scholes equation. So for a European call, which means I can only exercise it at expiry, the valuation is given by the risk neutral expectation of ST minus K positive. So if it is negative, then I get 0. If it is positive, then I get ST minus K. Because I always pay K and I get the stock. So the day zero valuation, if I want to evaluate it from the perspective of today at time small t, that will be at this discounting done on this expectation. So this expectation is what I expect to get on date capital T. So how much is it worth to me today? It will be equal to this. So this is the bank rate discounting that we have been doing. And the modeling exercise, we already know that directly that the process for the log stock price is a normal distribution. And what are the parameters? We are now at date time t, small t. So today's stock price is perfectly known. So I start from there. And then the log normal distribution property tells me that the expectation will be given by this r minus sigma square by 2 capital T minus t, and the variance will be given by sigma square capital T minus t. This we can evaluate from the first principles using the properties of the Brownian motion. So is this clear? Because this is the normal to log normal manipulation that, well, we know how to do. Is this log normal property known? So we have talked about the log normal distribution earlier. So if I start from time t, that is my 0th period value, which is known. And what is the change? The change will be given by this. And the volatility is proportional to the time interval. Here it is capital T minus small t. And the rate is taken as sigma square. So is the log normal familiar?
Yes, sir.
So then, using the Black-Scholes, we can explicitly find out this expectation quantity here, which is the price of a call option. And then we will discount it, of course. So I will just show you the final result, because this is the calculation part of it. This has not come out very well, but probably you can just see this. So this is C. I will just read it to you. This is C, which is the price of the European call option. And the final result will be C equals ST, which is the stock price now, times capital phi at D1. Capital phi is the CDF for the normal distribution, cumulative distribution function, minus K discounted e to the power minus RT minus T, capital phi of D2. Phi, capital phi, as I said, is the normal CDF, where what is D1 and D2? D1 is log of ST by K. K is the strike price, plus R plus sigma square by 2 capital T minus small t. And D2 is the same thing, but with a minus sign here. So it will be R minus sigma square by 2 capital T minus small t. So D2 and D1 are related through this equation. D2 is equal to D1 minus sigma times root over of T minus small t. So that is the final formula for the European call option price, which you find by using the Black-Scholes result on this particular expression here. And the algebraic details are worked out, but I think rather than going through them step by step, it would be nice for you to check it by yourself and confirm that this formula is indeed correct. It takes a little bit of calculus, but mostly mechanical type of calculus. So I will leave that for you to do later on, how to evaluate the integral and all that. But instead, what I will do is I will just look at this formula again, the final result. So what is the final result? The final result is two parts. One part is what you get with the probability of getting it. So this capital phi D1 is essentially the probability that the option will be exercised. And if it is exercised, you get the stock. So your payoff will be proportional to the stock price. Minus, this is the part where you are going to pay the strike price or it is not going to be exercised. So these two, so this capital K is the payment part. So I make this payment, and again it is appropriately discounted because the payment is made later on, and this is the associated probability. So this phi is coming from the normal distribution, of course. This D1 and D2 are the conditional probabilities for exercising. So again, our objective was to evaluate an European call option. So the only possible exercising date is the last date, terminal date. And we actually find the current value of that expectation. And you use the Black-Scholes formula, do some calculus to find out this particular expression here. And this expression essentially has two parts. One part is what you get with the corresponding probability, and this is what you pay with the corresponding probability. If I am looking at an American call option, where I have more freedom for exercising anytime from between now and capital T, in general, the value of American call option will be greater than or equal to that of the European call. So in general, capital C will be greater than or equal to small c. Small c is the European price. But we have already argued earlier in the discrete setup that if there are no dividends during the lifetime of the option, the call option, then it is never optimal to exercise early. So I will actually wait till the last date, till expiry. So effectively, the value of the American call option will be the same as the European to me. So if the value is the same, then the price will also be the same. And then for the no dividend case, capital C and small c will be equal. The same logic is actually not true for the put option. You can explicitly argue that even without dividends, put option may be exercised early. So in general, the value of an American put is strictly bit higher than European. So in yes.
Could you repeat the part? The value of American and European options will be same
For call or put?
for call. For call.
For call, if you remember the binomial model discussion we made earlier, we actually argued that if there are no dividends, it is never optimal to exercise a call option early. Even if you have an European option, an American option, you will wait for the last day to exercise. We have seen a couple of examples from Pliska, and then we gave an argument that if there are no dividends available, then effectively the American will behave exactly like the European. We have done that before, so maybe you have to go back to the discrete time calculations part for the binomial model.
Yeah, okay.
But even under the same situation, no dividend, etc., one can also show that a put option may be exercised early. There might be situations where you are better off exercising a put option before expiry date. So in general, capital P will be strictly greater than small p, where again capital P is the price of the American put and small p is the European put price. So because the exercise dates are multiple in case of American options, we have already said that you do not have closed form differential equations for American options. Like for European option, we have the Black-Scholes equation, and we can set up the PDE and solve it with some boundary conditions. For American options, we don't have that pleasure. What we do have are some bounds. Okay, so what do I know about the American call and put prices? For European options, of course, we have the put call parity. So small c and small p are exactly related through this equation. This we have discussed earlier, and we know this result. It was very useful, and basically 50% of calculation burden gets reduced. So you do the evaluation for all the call versions. The put versions are immediately available through this equation. For American options, we don't have this because there are multiple opportunities of exercise, but this result is still available. You can show that this is now capital C and capital P. You can show that the difference between the call and the put price is bounded between these quantities. So the lower bound is ST minus K, and the upper bound is ST minus K discounted. And again, to prove this result, you can use the same no arbitrage principle and arrive at this inequality. So recap, first of all, you should check and satisfy yourself that for the European call, whatever calculations are required, they will give you this result. This is the final result for the European call. That is one thing that you should check later. It's a bit of boring calculus, but not very complicated. And secondly, for the American options, we don't have the parity result because we don't have equality in all these cases, but we do have these bounds. So I will again leave it as a homework for you to check and verify these two inequalities. And the strategy is to again use the no arbitrage principle. So there will be some parity results that you should be able to use and arrive at this inequality. All right, so that's some homework. So I'm going to leave it to you to do. Okay, any questions on this so far? The use of the Black-Scholes. So we had the Black-Scholes equation over here, this PDE, and then we have used it on simple contracts. The forward contract was a trivial exercise just to check consistency. But then the European call, again, the definition is not complicated, but the calculation is slightly tedious. But if you are able to do it, then you should be able to verify this final result for yourself. And if you know small c, you also know small p because of the put call parity. So we need not explicitly compute it. For the American case, the homework is to verify these two bounds on the difference between the call and the put price. Okay. So now let me go on to some other issues before I move back to the calculus part. But this issue is a very important practical issue. Fama did a lot of empirical work with stock prices. And he checked that even though we think of a 3-month option contract, which is like 91 days, it is not really true that new information comes in on all the days of the week, because the stock market is only open 5 days a week. And he checked and tested that in actually one can show that the information generation happens much less over the weekends. So you can ignore those 2 days and think of a week, a calendar week, as basically consisting of 5 days. And by the same logic, you can think of a calendar year as consisting of 252 days. So what is the reason for this? Because whenever we are modeling stock prices using the Ito process, using the Brownian motion, we have to calibrate the volatility, the sigma square parameter. And what causes volatility? Again, we have discussed it before. Volatility is essentially caused by trading. So new information comes in, some people get some information, they trade, and through this trading, the price fluctuates. So the short-term fluctuation in the stock price is not really related to the fundamental, to the actual company that represents that stock, but it is actually due to trading. So some information coming to some people, they are reacting to it in different ways. As I said, everybody has their own subjective probability, but overall the market probability, Q probability, will determine prices. But that pricing operation can happen only, almost only, practically only when the trading is happening. And the trading happens over 5 days. So for volatility calculations, Fama prescribed that you should not look at the calendar days. You should look at number of trading days. So if you have a 3-month-long contract, instead of 91 days, your calculation should be based on 62 or 63 days. As many days the stock market is open in that 3-month period. So all the volatility calculations which happens here in this capital T minus T formula should be not in terms of calendar days, but in terms of trading days as prescribed by Fama. So whenever you get into empirical work with financial data, your calculations should be using these trading day count rather than the calendar day count. So I mention it here because we are more or less done with the theory and we will do some applications, but I expect you to actually start looking at the data now. We will not be discussing much data this semester in this course, because this course is primarily about the mathematical models, how they are set up, how they are used. But it all eventually will boil down to empirical work where you do the calibration, you do the estimation, you do the testing for models. And there, the general prescription is to use the number of trading days for any day count situation. So is this clear? So for 1 year, we will consider 252. For 1 week, we will consider 5 days. And 3 months will mean roughly 62 or 63 days. Because we have weekends and as well as some public holidays. Okay?
Yes,
Sir?
sir.
Yes?
On weekends, there might be some companies whose positions change and it gets added to the volatility. So are we completely ignoring that weekend information, or somehow it gets added to Monday's calculation?
See, you are absolutely right in the sense that new information do come in over weekend. Some trade is buffered. Remember that we talked about how the stock market works. The
Yeah.
orders are buffered over the weekends. So all this buffering is essentially generation of new information. But they all get executed only on Monday morning in the first 3-4 minutes. That's why we always say that the opening few minutes data should be ignored or handled with care. So you are correct in the sense that ignoring the weekend days completely is actually not right. But what Fama showed, and also it was verified later on by other people, that the rate of information accumulation is much less over the weekends. So what you can actually do is, maybe you can consider 1 week as 5 plus some 2 alpha days, where alpha is a fraction. But then it will again go back to calibrating that alpha. So most of the empirical exercises that people do in the financial market, they ignore the weekend altogether. But there are a few papers, some literature, where people have tried to calibrate what fraction should be taken for the close days. Okay.
Okay, sir.
Yeah. So if you Google or go to the archives, you will get some literature on this, but not much, because most of the financial empirical literature still relies on the typical 5-day week convention. It makes life very easy. You have a clear rule of counting. All right. So I will just talk about a few more results, integration results, which could be useful for us, and then stop today. So some useful stochastic integrals. So now I am going to talk about DB integrals explicitly. So again, these are essentially application of integration by parts, because any DB integral, we try to convert it to DT integral, and then evaluate the DT integral using the rectangles in the usual Ito integral sense. So what is the first result? The first result is what is the expectation of FTDB, GTDB. So it is like a covariance formula again over the same range A to B. Because if the range is different, we know what will happen. The calculation will happen only on the common range. So I want to find the covariance of this FDB integral and GDB integral. And if I use integration by parts inside on each of the integrals, both of these integrals can be converted to DT integrals and an additional constant term. But in expectation, they will cancel out. And the two DT integrals, their expectation you can evaluate using that earlier covariance formula. So we have already shown one covariance formula earlier, that sigma square T minus A, etc. So using that covariance formula, one can show that this expectation is equal to sigma square times FG dt, integral FG dt. So that is our first result. Again, you should be able to verify this result. It is not complicated, but just careful application of integration by parts result. The second result is just a corollary, that if I try to do this on disjoint intervals, A to B and C to D, where these two intervals are disjoint, then it will be certainly 0. That is straightforward. We already know that. What is a more important application of this formula is about the variance. So when I put F equal to G, I am essentially interested in the variance of this integral. And that is now given by sigma squared times integral of F squared dt. So this application is more important because, as I said, we are working with normal distribution. So in the end, we calculate expectation and variance. So to calculate variance of DB integrals, I have a nice formula. One simple use of this formula. Let's look at this particular Ito process with no DT integral, of course. It's a purely stochastic process. So xt is 0 to t, e to the power minus alpha t minus u d. So it is like a time discounting process. We will use it later when we are looking at forward contract valuations, current valuation, or sorry, present valuation, we will be using this kind of integrals for some finite t, 0 to t for some finite t. Now, expectation of xt will be 0. This we have already established. All the dv integrals have 0 expectation. We want to understand what is the autocovariance. So this is autocovariance, expectation between s and xt. So that will be given by the expectation of the product of these two integrals. So this is where the formula will come in. So we already have the formula. Our formula tells us how to convert the covariance of dv integrals to dt integral. So using that, this covariance I can write at sigma square, this f and g times the dt. So this becomes a dt integral, and I think it's not written here, but what we are using is s is less than or equal to t, so it is on the common part of the interval. So 0 to s. So for s less than or equal to t, common part is 0 to s. So this is my integral, and then I can easily evaluate that. So if I have a purely dv type Itô process, I know exactly what the discounted value process look like. So this is the discounted value process, time discounting, and I have been able to calculate the expectation and the covariance function for this one. And if I have the covariance, I also have the variance. That's straightforward. One small extension, not small, but a quick extension of this result is sometimes required to evaluate long-lived derivatives or infinitely lived derivatives. When we were going through the different types of derivatives, I discussed that there are some contracts which are infinitely lived. One example of such contract is a perpetuity. Another example of that contract is a life insurance, where the stopping time is uncertain. So in those cases, it would be difficult to restrict myself to a fixed small t, fixed finite small t. So sometimes it is useful to be able to consider infinite intervals on which I can define my integrals, which in real calculus we call improper integrals. So you have done improper integrals. Integrals over infinite.
Yes, sir.
Yeah, you have done that before. So, and you know that you need a little bit of care, some extra, excuse me. Some extra assumptions. So if I want to extend our dv type integrals to improper integrals, so I want to make sense of integrals of this type, minus infinity to infinity f dv. First of all, I will need all these functions to be square integrable, finite. The square integrals should be finite, because you know eventually I need the variance to be finite. If I do have that, one can show with appropriate theoretical care that the expectation of such improper integrals will still be 0, and the covariance, the autocovariance of these integrals will again be driven by the same kind of formula as before. But again, this itself is an improper integral. But I know because of these two assumptions, this is going to be a finite quantity. So if I want to handle infinitely lived financial contracts, I sometimes may need to handle infinite dv integrals over infinite range. So in those situations, this kind of improper integral formulation will be useful. But most of the time, we look at options and other finitely lived derivatives, and then it is a priori known what exactly is my capital T, what is my expiry date. And in that case, I can always work with finite intervals. So that's a clear-cut situation. All right. So any questions here? So again, these are operational formula, but this formula will be useful because I want to evaluate, finally I want to evaluate mean and covariance function of my solution processes. And in addition, we also talk about the improper version of this, because sometimes in some applications we look at infinitely lived contracts. In fact, a share itself is an infinitely lived contract. Any questions at this point? No questions? Okay. So then I will talk about one more important result. It is a result which is theoretical in nature, but it's again a very strong result. So it is like the Kolmogorov continuity theorem and the Ito's lemma. It's a very fundamental result. So what is the result? We have already shown that if a stochastic process X is given by this kind of a dV integral, then it's a martingale. So if there is no dt component, so in general, we are working with xt processes, which are etho processes. So for etho processes, I have a dt part and a dv part. But I also know that this kind of dv integrals are martingales. This we have actually shown earlier, correct? You remember this? This type of integrals are martingales.
Yes, sir.
So if my xt process does not have a dt term, then xt itself is a martingale. This we have established. What I am now going to say is something very, very powerful. I am saying that the converse is also true. What is the converse? The converse is, I know that this type of integrals are martingales, but there could be other type of martingales, other stochastic processes which has no connection with this kind of integrals. This theorem says no. This theorem says that if I have a martingale, then there will be a representation of this type for that martingale. And that is the martingale representation theorem. Again, a very fundamental result that suppose I have a Brownian motion B and MT is an FT adapted martingale and it is square integrable. So it is a nicely behaved adapted martingale. So if it's a martingale, then there will exist a unique stochastic process G, so that MT can be written as a dV integral of G. So it's not only true that the dV integrals are martingales, it is also true that all martingales can be written as dV integrals and uniquely represented. So it is not only existence, it is also unique. There is exactly one such representation. So any martingale, square integrable FT adapted martingale, can be written as a dV integral in a unique manner. Some of you have seen this result in different contexts. If you have done a formal probability course, you have seen the Radon-Nikodym derivative.
Yes, sir.
So this is the stochastic process version of that result. Because if I now notionally write this integral equation as a differential equation, I will be able to write dm equal to gdb. In the probability scenario, measure theory, I mean the formal probability theory, that is the Radon-Nikodym derivative. In the stochastic process scenario, this is the Martingale representation theory. Both are extremely fundamental results, very, very powerful results. Is the result clear? Because I'm not even going to attempt the proof. I'm just going to tell you what it is. So does it make sense? So once again, I just repeat that all the dB integrals we have shown to be martingales. That is from the properties of those integrals. But now we are stating that every martingale can be represented, uniquely represented as a dB integral of a suitable stochastic process. So I have a corresponding G function and I can write any martingale as a GdB integral. And you can see that this is actually a very, very powerful, very strong theorem. So basically what is happening is, if you look at it intuitively, a martingale is basically sum of zero mean increments, because conditional expectations are always equal to the last available value. So the intuitive idea for a martingale is that the conditional expectation is the same as what I see today. So the increment in future always has zero expectation. So I can think of martingales as sum of such mean zero increments. And what is the rate of change or the slope of that? That slope is given by this function g. So g in effect acts as the slope or the derivative of this martingale. So if you sort of visualize what would be a derivative of a martingale, then g acts as the derivative of this martingale. So that gives me the slope. But it's a slope on zero expectation increments. So however much I add on here, the expectation will always remain zero. And conditional expectation will always remain at the last available value. And that's what gives it the Radon-Nikodym interpretation, that if my martingale process is empty, then G can be thought of as the density function of N. Because it's notionally, that's how we try to understand the density function. The relationship between a distribution function and the density function. And that's the connection we make in the Radon-Nikodym derivative. Here also for a stochastic process, we have a density function. Of course, it is time dependent because G is not only a function of omega, it is also a function of S. So G gives the density of MT at time t. Okay, so I will stop here. We will continue on Wednesday, unless you want to ask me something. So if there are some questions, I can take them, or we can discuss on Wednesday. Wednesday we will make some more progress. But again, I repeat, it's very important that you read the textbooks, the relevant chapters and sections, and start looking at the exercises. Because some of the exercises are very, very easy, but if you do them, your conceptual clarity will improve a lot. Because we have been talking about a lot of new concepts, we are not giving proofs. Sometimes we are not giving any proof at all, just making statements. So some of the intuitions might be fuzzy. So if you start doing the exercises, that intuition will come.